Now that I think I'm on camera,
Next Wednesday.
let's make sure that we're not repeating. Yeah, okay, we're good. Okay. So now, last time we met, we were talking about the law of reflection. And we had that theta instant, theta reflected. Our law of reflection is that theta instant is theta reflected. Yay? So in our problem session problems, I did a couple, I did at least one of these. So is this sort of okay?
Yes.
All right, so if I have a mirror that, so one horizontal, one vertical, the nice thing about this is that note, let me do this larger. So this is theta 1, this is theta 1 also. And when I say theta instant, theta reflected, I mean with respect to the normal. Yeah?
Okay.
So if this is theta 1, what is this angle?
90 minus theta 1.
Right, and so note that if I draw another normal here, what's true about these two normals? They form a 90 degree, right? So I could call this theta 2. I know this is also theta 2. Yeah? But what else can I say about theta 2? Well, note that it's equal to 90 minus theta 1. So, what is this angle?
90 minus theta 1.
It's also theta 2 or 90 minus theta 1, right? So what? Cleansed by fire, it's the only way. So what can I say about this instant ray and this ultimately reflected ray?
Parallel?
They're parallel to each other, right?
Yeah.
So this is the 2D case. You could also make, oh good golly, Somewhere MC Escher is crying. You could also make a 3D version of this
Okay.
if you really, really believe, right?
Like a door. Open it.
This has the net result of however it's instant, it's going to reflect back anti-parallel. Okay, we call that a corner cube,
Oh,
a corner cube mirror. We left stuff like that on the moon because it's what people do, right? We go places and we leave garbage. This wasn't even garbage, right? This was an attempt.
Scientific garbage.
Yeah. We use stuff like that to keep track of how far away the moon is. The moon is creeping ever so slightly further away from us. So, do you guys know what tidal locking is?
Yes.
So, tidal locking is a special gravitational orbit case, right? It's the case where the thing always sits over the same point on the parent it's orbiting. So the moon is not tidally locked to us, but partially. Has anyone ever heard the expression "the man in the moon"? No. Maybe you've heard of the little bunny rabbit on the moon.
Oh, yeah.
I heard of the
It's
man.
a Chinese word.
It is. Well, you said you didn't know the man in the moon, so I gave you the bunny. So, it's familiar, right? The man in the moon, the bunny. You always see the same side of the moon. Always. Unless you're one of those fortunate people who got to take a ship around the moon. You're all too young for that. But yeah. That said, Earth, moon, the same side of the moon always faces Earth. The moon has a crust made of fairly low density material. The inner part of the moon is denser, but it's offset so that the moon has a heavy side. If any baseball fans?
Oa's.
Yeah, sure. If I get my baseball back, then sure, go A's. But right now they're canceling games. Be really ticked off if that winds up being the case.
Chicken nap.
And I'm not saying that me being in a bad mood will make your exams harder, but I'm not saying that either. If we tied a baseball bat to a string, or drilled through the center of length, hung it from the ceiling, and let go, what would it do?
Tip towards the heavier side?
What would the heavier side do?
Okay?
Point down towards the ground, yeah? Does that make sense?
Yeah.
Well, why? Gravitational torque, right? So the heavier side would rotate downwards, yeah.
Yeah.
Moon has a heavier side, so
Oh,
that
really?
the same face of the moon always hangs down towards the Earth.
Oh.
So if we always see the same side of the moon, does it rotate?
both of them
It
rotate.
does
the same-
rotate,
The Earth
must
rotates, the
rotate.
moon also rotates.
but we're also rotating at a similar.
That's not quite the, so if, I can't believe I'm doing this in front of a camera. I can't believe I dressed up. By the way, this is me dressing up. One of the only benefits of my job is I haven't worn a tie other than a wedding or a funeral since 2007 when I got this job. That's not true. I went to a conference last year where SETI made me wear a tie. But very, very rarely. So if you were sitting in this chair, you're Earth, I'm the moon. If I don't rotate at all, right now I'm facing Earth. If I don't rotate at all, then at some point you would see every side of me, right? Yeah. So I must rotate, otherwise, again, you wouldn't just see my masked face, you would.
We see
So does it rotate with
30,
according
160
to
degrees.
Earth's axis?
So but if I rotate too fast, you also,
So
I know,
Would this be similar?
I should have at least taken this all the way off camera first.
So, question.
Regrets. I
Would
have a
this be
few.
similar to like if you're filming like a helicopter and you manage to get the frames per second correctly, you can it looks
Make it
it's
look
just
like the
floating?
blade is still.
Is that
Yeah.
like the similar process?
Same idea.
Okay.
So here, if I want to make sure that, maybe this is one of my, by the way, even when I tried to dress slightly nicer, right? No, it's still plaid. But maybe this is one of my plaid shirts that has like a tear in the back, which you can really only use in Zoom. So maybe I don't want this person to see my back. Then what do I have to do? Well, if I don't rotate at all, that didn't work. If I rotate too fast, that didn't work. The fact that I said too fast implies that there is a Goldilocks answer, right? So I need to complete one rotation in the same amount of time it takes me to walk all the way around. So and now that person has no idea whether the back of this shirt is ripped or not, right? Does that make sense? So the moon, how long does it take moon to complete one lap around Earth? A moon. Exactly. So that is the orbital period. What's the rotational period of the moon? It's also a moon. So for Earth, how long does it take to complete a lap around Sun?
365.
A year, right? How long does it take to complete one rotation on a spin axis?
24.
A day, right? Yay?
Yeah.
For moon, those two numbers are the same. Because it's not tidally locked, but there is a little bit of that incentive going on. Yeah? Does that make sense?
Yes.
Well, we could actually minimize the energy by fully tidally locking this. That's not true, but that's the trend. So in order for moon to not only just show us the same face all day, every day, but also to live directly above my house, it wouldn't do that. But I don't live close enough to the equator. But what would have to happen in order for it not only to show me the same face all day, every day, but also not rise and set, just always be over over one spot.
It would need to be perfectly balanced.
What would have to happen to the moon's orbital period or rotational period, since they're the same?
Rotational period is here.
It would have to match Earth's rotational period, right? And so,
The angular speed should be relatively in a certain ratio, like kind of, sort of.
yeah, so what we need is
W something.
for moon to complete one lap in the same amount of time it takes for Earth to spin once. Yeah? Does that make sense?
Yes.
So, this won't ever happen. But the trend is in that direction. If you were alive a few billion years ago, one, you might have been in my kindergarten class, but two, the day was much, much shorter. In order for that to happen, moon is slowly creeping away, but I liked what Susan said. She was talking about energy, she was talking about rotational momentum. The rotational momentum has to be conserved, right? So if moon is gaining rotational momentum, what else has to happen?
Somebody is losing momentum.
Who's losing?
Earth.
Earth. So as moon slowly gets further away, it adds about a second every couple thousand years to the day. That probably doesn't sound like much, but over a few billion years, that's hours. The day is hours longer now, many hours longer now than it was a few billion years ago. So if it feels like this lecture will never end, this day will never end, my dull droning monotone is just going to keep going on and on and on and on and on. Blame the moon. But all that's to say, we watch the position of the moon with corner cube mirrors. We shoot lasers at it and wait for the pulse to come back. Yay enough? You guys are okay with this idea of following the geometry?
Yeah.
I could bend this, I could tilt this mirror a little and you'd still be able to follow the geometry. I believe in you. Okay. All right, then reflection was when light traveling in one medium encounters the boundary of a second medium, and at least some of that light ray is reflected back into the original medium. Yay? Now I want to talk about refraction. Refraction is what happens when that light ray traveling in one medium encounters the boundary of a second medium, and at least some of it is transmitted into the new medium. So refraction is following the path of the ray that follows, that travels into the new medium. So, oh goodness, do I have to write all this out? It's killing me. Okay, so this is a great example of why math exists. Don't show this to Carol. Because that is a lot to write, but I can say the same much, much more elegantly and simply in math, right? So here is our medium 1. I'll do this for air and glass. And medium 2. So
Do you need a jacket? Oh.
So we just talked about reflection, where I'll call this theta 1, where some of the ray stays in the original medium and it reflects with an angle equal to the instant. Is that ink dark enough that you guys can see it? Yeah? Okay. But some of it is actually transmitted. And so what we find is that sine theta 2 over sine theta 1 needs to equal V2 over V1 is some constant. So yay, sort of yay at least.
What those B stands for?
The speed of
Speed.
the ray or the wave in the medium. So we are going to define n, an index of refraction, as the speed of light in vacuum over the speed of light in the medium. And so this winds up looking like C over V. What I will tell you is that air is sparse enough that the speed of light in vacuum is just a tiny little bit faster than the speed of light in air. And so, for the most part, when we talk about speed of light in air, I'm still going to pretend it's c. And so, here, I'll do it this way. N for air is about 1.000293, right? So you can see that that implies that the speed of light in vacuum compared to the speed of light in air is pretty darn close. N for crown glass is about 1.52. N for flint glass is about 1.66. And N for water is about 1.33. Yay?
What is the first glass thing?
Crown glass. Just different ingredients. Different impurities. So, if our working assumption is that frequency is preserved, but wavelength will change, and so we're going to say that F1 is equal to F2 is just equal to F. In our case. And we have that wave speed goes as F lambda. So then V1 is equal to F1 lambda 1 or F lambda 1. And V2 is F lambda 2. Then we also have that N, well, let me do it more gradually.
Wow, it's a giant.
If I want lambda 1 divided by lambda 2, so lambda 1 is V1 over F, lambda 2 is V2 over F. So did I get that right? Yeah? But
F is
frequency.
oh,
N goes as C over V, so
What's the lambda?
wavelength.
lambda.
What is it?
Wavelength,
Oh,
sorry.
So F1 and F2 are the frequencies of the wavelength at the mediums that we're talking about in this case, air and glass.
So, yeah, we're going from air to glass. And so everything, so medium 1 here is air, medium 2 is glass. So everything with a subscript 1 is for air, everything with a subscript 2 is for glass. But this applies more broadly than just that. But we also have that N1, I don't know why I'm being this wasteful of our word. That N1 is equal to C over V1, and the N2 is not C1, C over V2. Yay? And so we can say that V1 is C over N1. And that V2 is C over N2. And so if we plug in, we get C over F times 1 over N1 divided by C over F times 1 over N2. Is that all right? Which is N2 over N1. Yes, no, maybe so. Combining that with the statement, sine theta 2 over sine theta 1 needs to equal V2 over V1. But we just said V2 over V1. Wait. I didn't need to go through all that work, did I? V2 over V1 I could have just written as C over N2 over C over N1 is N1 over N2. Okay? And so in that case, N1 sine theta 1 is N2 sine theta 2. Not untrue, just not necessary to get where I was trying to go here. So this is what we refer to as Snell's law. So, and I think this week we'll do a lab where we'll examine Snell's law, we'll examine the law of reflection, we'll go a little past this to even looking at some optical devices. So, questions, comments, concerns?
So we can just use the results. We do not
Oh, yeah.
improve, right? Okay.
So far, so good.
Yeah.
All right.
Does it has a special name or it's just
It's the index of refraction.
index of refraction?
What's the guy's name? Slayer? Slayer's not?
Snell.
Oh, Snell.
So, wanted to go through some interference stuff, and specifically Young's double slit experiment. So we talked about this a little last time, I think. So if we have our plane waves approaching a board with two small slits cut into it, then we see, as we looked at a little bit last time, that we get not my best work, but you guys will forgive me. You're very kind. If we have a viewing screen over here, what we're going to find is that directly centered, we get a max. And then satellited off of this, we get a min, either direction. And we get another max. And it alternates. And this is owed to constructive and destructive interference. So if we were to think of this as in terms of travel distance, so if you'll allow me to kind of really block diagram this. Let's assume that we have a coherent light source. When I say coherent, coherent and monochromatic, I mean single wavelength, and the sources are in phase with each other. They both start with the same phase angle. They both start either at peaks, they both start either at troughs, or wherever they start, they're both starting at that same point. Well, and that's the beauty of this double slit idea, right, is that you're taking one light source, which presumably over the spacing between the slits is still in phase with itself, right? It's one thing. And as long as you're not looking over a very wide region, it's at least a decent expectation that the light that comes through those is in phase. Well, then if we were looking at that, compare this travel distance to this travel distance.
You're equal.
They're equal, right, if it's exactly in the middle of those two slits. And if we were to think of this in terms of wavelengths, right?
It's fine.
The thought that counts, right? Note that they both arrive doing the same thing, because they both traveled the same distance, right? You can fit the same number of wavelengths on that path, on the upper path or the lower path. Yay or not yay? So they started out in phase, and they wind up in phase, so they're going to add together. Peaks will add to peaks, valleys will add to valleys, right? That makes sense? And so that's why you get a maximum here. So we could also argue that if, oh good golly, if we make I'm going to call this 1 and 2. If we pick some point off center, right, that we can institute a path length difference. Now which one travels farther? Is R1 greater or R2?
R2?
R2 is, right? So if R2 minus R1 is equal to, so that's the extra distance, right? So we could imagine, you know, that one of these is just traveling some extra path length, R2 minus R1. If R2 minus R1 is equivalent to some integer plus half number of wavelengths, so then what's going to happen if they started out in phase?
Destructive interference.
We'll get destructive interference because they're arriving out of phase, right? If they start out in phase like this, peaks line up with peaks, valleys line up with valleys, if when they arrive like that, peak lines up with valley, valley lines up with peak. These guys partially or fully cancel, right? And we'll get our first minimum, yeah? But then if I keep going, such that that R2 minus R1 is equal to n times lambda, what will I get? Now the difference between these
More constructive.
is they started out in phase, they're going to wind up in phase 2. Yeah? Imagine that this isn't imagine. This is probably the stuff of nightmares. But imagine that I had a twin brother. I'm the evil one. I get to be the evil twin. But we both are as robotic as can be. And so if I start with my left foot, I also make it to the end with my left foot. Yeah? If instead, the good twin, right? So good twin is starting 2 steps in front of where I started. Still makes it there with the left foot. Yeah? The extra travel distance is just one set of left and right. Yeah? We could also do that for any extra set of 2 steps. Does that make sense? And so this top one corresponds to destructive interference. This lower one corresponds to constructive interference.
The 2 troughs add up. It's still light.
Sure. As long as they arrive in phase, then it's going to wind up being constructive interference.
At some point, they're both 0. Like
Yes.
they're both
But the way that we describe brightness is time